हेलो बच्चों। हेलो बच्चों, सत श्री अकाल and namaste from my side, right? So today we are back, right, into the ultimate recap, the Trump, okay, the ultimate recap, right, for the magnetism and matter lecture. And as usual, we are going to follow the reverse engineering. The reverse engineering states that things are quite simple. Entire chapter we are going to see into the lesson span of the 50-55 minutes, and we are going to cover up the each and every concept through sums. Sums are only the way through which the each and every concept can be covered easily, right? Okay, so guys, I think without wasting our time, let's move on to it directly, right? Let's move on to it. Okay, so the agenda of today's lecture will be the practice question as usual. Okay, that was asked in NEET 2017. This was asked in NEET 2017. If theta 1 and theta 2 be the apparent angles of the dip observed in two vertical planes at right angle. If theta 1 and theta 2 be apparent angles of the dip observed in two planes at the right angles to each other, then the true angle of the dip will be what? C. Again, we are going to repeat the concept of apparent dip and true dip. In previous session of the earth magnetism, we have seen only one plane, that was angle beta with respect to the magnetic meridian. Don't get worried. Okay, don't get worried. Things are gonna be like that. Again, we are going to, but in this we are having the two planes. The concept of the true dip and apparent dip, it is going to be same only. Okay, but how things are getting differed, it is important to understand. Okay, so for this, I think I will give you the 1 minute of the time, because the concept of this we have already seen, but it is important, right? Okay, just 1 to 2 questions before I'm going to give you all the time, then we'll move forward without countdowns. Let's repeat this question, that theta 1 and theta 2 be the apparent angles of the dip observed in the two vertical planes. Theta is a true angle of the dip. So let's revise this concept first. Okay. This is magnetic meridian they are talking about. Okay. This is the horizontal component of the magnetic meridian, right? And this one is the vertical component of the magnetic meridian. Okay. One is a horizontal component, second is a vertical component. Okay. This is magnetic meridian. So here whatsoever the angle it is coming, this is a net magnetic field. Okay, and this whatsoever the angle that is coming, that is theta. Okay, it is the true dip. Okay, so here I am going to write it down, the definition of the true dip. Okay, into the bottom, the true dip, that is equal to tan of theta, that is vertical component by horizontal component of the magnetic field. Yes or no? Okay, this is the mm stands for magnetic meridian. Mm stands for magnetic meridian. Now, the angle of the apparent dip comes when the plane is perpendicular, or I'm not saying perpendicular, one plane is at angle theta with respect to the magnetic meridian. But in this question, they have taken the two planes. In this question, they have taken the two planes. So I am going to write it down here. This is actual magnetic meridian. Okay, this differentiation, it is important, else you are going to get stuck. Okay, and the concept of the apparent dip holds the prominent position into the NEET syllabus. If it is asked into the 2017, that is having the highest possibility to come up into an upcoming examination. Yes, actual magnetic meridian, yes or no? This is an actual magnetic meridian. Now question states that there are two planes perpendicular with respect to each other. Okay, two planes are perpendicular, they are imaginary planes. That shows the apparent angle dip. So again I am going to write it down. Suppose the white color is the magnetic meridian. Okay, so we are having one plane, see. Like this way. Okay, one plane at this way. Second plane is this way. As the two phases of the coin. Okay, not two phases, two parts like this way, and in between we are having the magnetic meridian. Okay, should I change the color? So I think it would be more helpful to understand, right? If I change the color, then it would be more helpful to understand. Okay, yes or no, guys? Okay, so let's keep this as a green color. Okay, now we are able to understand. Okay, the angle between this is plane number 1. Okay, having the apparent dip angle as theta1. This is plane number 2, that is having the apparent dip angle as theta2. Angle between them is 90. Suppose, right, the one plane makes angle alpha. The total is 90 degrees, so another will make 90 minus alpha. This is all with respect to the magnetic meridian that is going on. All with respect to the magnetic meridian is going on. Okay, if you are able to understand this concept, then and then you are going to, okay, here, okay, the mathematical part is not as much difficult as what we are thinking. Okay, mathematical part is not difficult, but to imagine the situation, it is a difficult part. Okay, mathematical part is not difficult, to imagine the situation is the difficult part. Okay, and again many number of the students, right, writing down into the comment box, sir, we are not able to understand and we are not able to write down the notes. So I think more than 1.5 months went on, and we are teaching regularly, and suddenly if some students are commenting, okay, the students, those who are teaching with me from the beginning of the 12th syllabus, they are always aware Indrajit sir moves from right side and like this way, because I have a habit, because I am going to move on from this now. Okay, I am not able to explain well what as it's going on. Okay, and all the time whatever you want to note it down, I always used to mention, but note this mandatory stuff, bacha note this mandatory stuff, this kind of the thing. And the notes into the PDF formats are also available, and they are easily accessible, and they are easily like you are able to easily understand. Okay, so in this, one is alpha, second is 90 minus alpha. So I want to tell you all that suppose this is BH. So can I say this is BH cos of alpha, and this one is BH sine of alpha. The vertical component of the magnetic field remains same. Okay, this is a horizontal component, na? This is only the concept of the apparent dip is the plane that makes angle alpha with respect to the magnetic meridian, such a way that vertical components remain same, but the horizontal component of the magnetic field changes by the angle. Suppose it is tilted at angle alpha, then one component is BH cos alpha, another component is BH sin alpha. The vertical component is going to be same. Okay, so let's move on. First calculation will go on for magnetic meridian according to the formula of true dip. Okay, tan of theta, that is equal to vertical component by the horizontal component. Consider this as equation number 1. Okay, this is the concept of true dip. The second thing that comes upon for plane number 1. For plane number 1, the apparent dip is like tan of theta 1. Apparent dip is like tan of theta 1, that is equal to vertical component remains same. But in this case, the horizontal components became BH cos of alpha. Okay. Can I consider this as equation number 2? Can I consider this as equation number 1? Yes or no, guys? Can I consider above as equation number 1, below as equation number 2? Now this is an apparent dip for the plane number 1. Similarly, see why I used to make on all of these arrows, right? Because we are moving on to this side. This is a kind of a notification. Okay. For plane number 2, and suddenly after 1.5 months, the name of the student that I haven't read, if they are coming up, it's okay. We welcoming you all. Okay, but please start from the beginning. It is my those who are watching this lecture directly. Okay, I request them to start from the beginning of the 12th syllabus. It would be quite helpful, right? Okay, so here that is tan of theta 2, the second apparent dip. Again, the vertical component is going to be same, but the horizontal component, here it is BH cos alpha, here it is going to be BH sin alpha. Can I consider this as equation number 3? Yes, I can consider this as equation number 3. Can I rewrite equation number 2 and 3? See, BV by BH is tan theta. Can I replace this into the equation number 1? So, tan theta of 1, that is going to be tan of theta, right, whole divided by cos of alpha. And similarly, tan of theta 2, it is going to be tan of theta whole divided by sin of alpha. Let's make sin alpha and cos alpha as a main term. Again, I am rephrasing. Cos of alpha is equal to tan of theta by tan of theta 1. Cos of alpha is equal to tan of theta, and here sin of alpha is equal to tan of theta whole divided by tan of theta 2. Okay. Can I consider this as equation number 4? Can I consider this as equation number 5? Squaring and adding equation number 4 and equation number 5. Okay. Cos alpha tan theta by tan theta 1. So this is going to be cos square alpha plus sin square alpha. So obviously that is going to be 1. Right? According to Drigo. Cos square alpha, it is going to be tan theta by tan theta 1. So tan square theta by tan square theta 1 plus tan square theta whole divided by tan square theta 2, that is going to be 1. Right. So finally resolving this, you are going to get cot square theta 1. Okay, if you want to know how it went on, 1 by tan is equal to cot. Tan is inverse of cot. So can I say, make it tan square theta, that is 1 by tan square theta 1 plus 1 by tan square theta 2. Okay, that is 1. So it is 1 by tan square theta 1 plus 1 by tan square theta 2 is equal to 1 by tan square theta. 1 by tan is cot. Okay. So final answer you are going to be like that. Okay. cot square theta 1 plus cot square theta 2 is equal to cot square theta. Okay, theta is true dip, apparent dip of first plane, apparent dip of second plane. These two planes are at right angle with respect to each other. Mark my words, the relation between two plane is given, not a plane with magnetic meridian. Okay, this is an important difference that you all should know about it. I understand the question is bit long, but things moves like this way only. Okay, it is important. So cot square theta 1 plus cot square theta 2, this is going to be the perfect answer for this specific question. Right? Perfect answer for this specific question. Yes or no, guys? Okay. This is slide number 1 for notes. This is slide number 2. Always moves from right to left. And this is slide number 3. And this is question number 2. Again, the question that was asked in NEET 2017. Before moving on to this, we will actually understand the concept of the work done and everything. I have taught into the torque. Many students might not have watched the entire lecture, but again I am going to teach, don't get worried. Okay, I saw that previous session, but many students are like that na. Okay, the number of the students, those who are following, see, I am not complaining, guys. Again and again I am saying I am not complaining. I am just saying for your good purpose. The number of the students, those who are immediately jumping off the 5th chapter. Okay, a day-to-day life I am going to take. Let's take an example of Pathan movie that went on right now. Okay, after 15 minutes, if you are entering into the cinema hall, nothing is going to work. Suppose a thriller I am talking about, the most suspense thriller film you are watching, and when you are entering the cinema hall after 15 minutes, okay, then it's not even the fault of cinema, the film, not even the fault of yours. You might have got stuck somewhere. As of that reason, you entered the late. It's the natural, they are the natural consequences. The film is not aware of because the virtual thing is going on. Right? And even the theater is not aware of because he can't call each and every person. He can't have the pickup facility for each and every person at the right time. Okay. So this kind of misunderstanding always happens. So it is important to clear all of those stuff. Okay, so the number of the students those who are directly watching this lecture, it means you are approximately 5 chapters late in the syllabus. So immediately move back, cover your backlogs and jump off here. This thing I have already taught, but again I am going to teach so that it will be quite helpful for you all. A 250 turn rectangular coil of length 2.1 centimeter and width 1.25 carries a current of 85 microampere. It is subjected to the magnetic field strength of 0.85 Tesla. Work done in rotating the coil by 180 degree against the torque. This is the important statement. In the question, the last statement itself explains you all. The last statement itself explains you all. Work done for rotating the coil by 180 degree against the torque. Right. Let's move on to the actual concept first. The same concept we have seen into the electrostatics. Same I have repeated into the previous session and same we are going to move forward today. Right? See, I am taking an example of a loop. Right? I am taking an example of a loop. Okay? A loop is kept into an external magnetic field. A loop is kept into an external magnetic field like this way. Parallel to the plane. Okay? External magnetic field, and that is constant. A loop is kept. Okay? The situation moves on like this way. I'm going to demonstrate you. Okay? This is an external magnetic field, and like this way parallel to the plane, the loop is kept. Yes or no, guys? Now what happens here? Okay, what happens here? So things like, suppose if I am talking about the small current element here, suppose the current is in the clockwise direction. Okay, or you can say suppose the current it is in any direction you want to take, it's not a matter. Okay, for understanding purpose we have to move on. Suppose the ideal is like this way. This is the direction of the current element, right? And this is the direction of the magnetic field. Okay, if we are keeping hands on ideal, curling your fingers, the magnetic force is coming into the downward direction to the loop. So magnetic field is this, ideal is inside, magnetic force on the one side of the loop, it is acting downwards. Similarly, what happens if I am talking about the another side? Okay, now this you all are aware of how we identify the direction of the magnetic force. We all are aware of the formula Fm, that is equal to IDL, right, cross B. Okay, the direction of the cross product of the current element and the magnetic field gives the direction of force. Okay, this we are aware of. Okay, if you want to take the direction of the velocity, then also it is going to be same in this case, right? Some students might be having the habit, na sir, V cross B, V cross B, V cross B. It's okay, whatsoever you want to take. So onto the one edge of the loop, the magnetic force is acting into the downward direction. Similarly, on the another edge of the loop, the magnetic force is acting into the upward direction. So this thing we have seen into the case of, right, into the case of external magnetic field, when it is kept constant onto the two edges of the loop. Suppose the loop is hinged at this point. Let us take an example. Okay, this hinged, it is just for the understanding purpose. Don't don't fix it into your mind, right? One force is acting into the downward direction, one force is acting into the upward direction. So in this case, what happens? According to the translational equilibrium, according to the translational equilibrium, right, the summation of the all forces is going to be zero in y direction. One is downward, one is upward. So the net force into the y direction is completely zero. Yes or no? Net force into the y direction is completely zero. Okay. Now what happens? Net torque is not zero. This thing we have already seen. Okay. Net torque is not zero. Okay. Just this thing you have seen into the 11th standard, right? Rotational motion, concept of translational equilibrium, concept of rotational equilibrium. Okay. This thing you have done, I am just repeating. Just grab this arrow, try to pull. This loop will rotate like this way. Just grab this arrow, try to pull. the loop will rotate like this way. It means that net force is 0, but net torque is not 0. So in this case, we have already seen the net torque can be given as M cross B or MB sine of theta unit vector N. Now what is work done? Like we have seen this into the gravitational, we have seen this into the rotation, we have seen this into the electrostatics. Against this torque, again see now here, in this case, the torque will be into the clockwise direction. Right now, like this way. So this rotates like this way, in clockwise direction. I want to stop this rotation. I am hating this force. I want to stop that. I am hating this force. I want to stop that. So as of that reason, I have given the task to external force. Do the work. I have given the task to external force. Do the work. Against the torque to stop the rotation of the coil. Okay, this is an actual concept that we are going on, guys. Okay, the work is done. The torque and work here both are acting into the opposite manner. Okay, when object is kept into the coil, it rotates. Against the rotation, work is done to stop the rotation. It means that the amount of the torque we are having, the same amount of the work is applied into the opposite direction, it will stop rotating. So for that, I have given the task to the external agent to do the work against the torque to stop the rotation. So the external agent told me, I have to do integration, sir. Okay, I said MB sine of theta d theta. Okay, do the integration. So by doing the integration, he got it as MB sine of theta d theta. Now work the external agent asked me, sir, from which angle to which angle? I told, stop this rotation from theta 1 to theta 2. Just or do the work or stop the rotation. Two possibilities are. Okay. Do the external agent did. Okay. He said, sir, suppose if you want to do the work from theta 1 to theta 2. Two kind of work done we can do. Na? Even we can rotate the coil also. And we can do against the torque. So this is equal to MB sine of theta d of theta. So here the work done, it is equal to MB, right, cos of theta 2 minus cos of theta 1. Suppose if work is done from, if it is opposing, right, then the work will be done from theta 2 to theta 1. So this is going to be changed like, okay, it is just a man. Now this work done, it is stored into the form of the potential energy because everything here it is conservative. So U, it becomes MB cos of theta 1 minus cos of theta 2. Okay, so this is the concept of work done against the torque. Work done against the torque, that thing is mentioned into the question. Now in this, we are having the two possibilities. Okay, what does the question, so this was the explanation of the concept, right? What does the question say? Work done for rotating the coil by 180 degree against the torque. Rotating the coil by 180 degree against the torque. This is the work done MB cos of theta 1 minus cos of theta 2. 180 degree. It means that initially angle was 0. Final it was rotated by 180 degree. Initial angle was 0. Final it was rotated by 180 degree. So work done, it is going to be MB cos of 0 is 1. 180 is minus 1. Okay, so this work done, it is going to be 2 MB. So this is 2 into current into area into the magnetic field. Is it having the number of turns? Yes. Then it is going to be multiplied by n. Now you have to just replace the values and get the answer. In this case, only formula of torque is important, formula of potential energy is important, and stable and unstable equilibrium is important. That is going to come up into an upcoming, that is going to be an upcoming question. So on replacing these values, okay, so it is 2. What is the value of the current that is flowing? 85 microampere length. Okay, yeah, slowly we are getting 85 microampere. So 85 into 10 to the power minus 6, right? Okay, number of turns are 250. Okay, area and magnetic field. Magnetic field is 0.85 Tesla. 1.25 into 2.1. 1.25 2.1 into 10 to the power minus 4 into 0.85. We have just replaced all of those values. Okay, we have replaced all of those values. Okay, 0.85 into 250. So solving this, the work done, it is going to be approximately 9.1 microjoule. And this is going to be the perfect answer for this specific solution. So first of all, I explained you all the concept. And this is the solution, the number of the students, those who are not able to. Okay, note this mandatory stuff, guys. Again and again, I used to tell in each and every lecture, I'm telling you also. Okay. D is the perfect answer. Now things are going to be quite easy for you all. See. Magnetic needle suspended parallel to the magnetic field requires √3 of work done to rotate through 60 degree. Torque needed to maintain the needle in its position will be what? Again, see, work done and torque are against. In maximum number of the cases, work done and torque, they are against of it always. Work done is √3 joule. Directly we are going to, here now we are aware of the formula. W is equal to M of B cos of theta 1 minus cos of theta 2. Work done is √3 joule from 0 degree to 60 degree. Rotation is done by 60 degree. So this is MB cos of 0 degree minus cos of 60 degree. Okay, theta 1 was 0, theta 2 is 60. That's why the rotation happened from 0 to 60. And as of that reason, they have written it turned by 60. Turned by 60 means 0 to 60. So √3 is equal to MB 1 minus half. So √3 is equal to MB by 2. Can I consider this as equation number 1? Now things are going to be quite easy. This is the first part of the solution. Now we are moving forward to the second part, to the left side. As usual, the habit of Indrajit sir. Torque needed to maintain the position. What will be theta? See, work done in rotating 0 to 60. Now at this moment, torque needed to maintain the position. It means here the angle is going to be 60 degree final. First it was 0. It turned to 60. After turning to 60, torque is applied to maintain the position. So at 60 degree torque is applied na. At 60 degree the position is getting maintained sin 60. So tau is equal to MB sin 60 √3 by 2. Can I replace MB by 2 as √3? So torque is √3 into √3 is equal to 3 Newton meter. So torque required is 3 Newton meter. Is another unit. Joule is also the perfect answer for this specific question. It's very simple it is. Okay, now hope so you will understand. Apart from this, only the question of stable and unstable equilibrium is going to come, and I'm going to explain that part. Don't get worried. Okay, I'm going to explain that part. Don't get worried. I have kept into the silent, and then again phone hangs. It's now see again the question that has been asked in NEET 2030. Very awesome question. Wallah al habibi, master question. How to calculate the magnetic moment for the arc? For the straight bar magnets, we are aware of. But if the bar magnets are tilted at some angle, how you are going to calculate is a very awesome thing. A bar magnet of length L and magnetic dipole moment M is bent into the form of arc as shown into the figure. It is bent into the form of an arc as shown into the figure. The new magnetic dipole moment will be what? The new magnetic dipole moment will be what? Yes or no, guys? The new magnetic dipole moment will be what? See, initially magnet is like this way. Okay, let's say this is north pole, this is south pole, the length of the magnet is L, the pole strength is M, right? So the magnetic moment capital M is small ml. Can I consider this as equation number 1? Solution. Can I consider this as equation number 1? Yes or no? Now it is bent into the form of the circle. How things moves on. Okay, consider this is equation number 1. Now it is bent into the form of circle that extends an arc of 60 degree. Okay, that extends an arc of 60 degree. This is one pole, this is another pole. Sorry for this extra purpose. This is just for the explanation. Okay. Now what happens? This is R, this is R. Mark my words, into the formula capital M is equal to M into L dash. This is a new magnetic moment for this. M dash is a new magnetic moment, L dash is a new length. That new length is always the shortest distance between the two edges of the magnet. This thing we have seen into the concept of force. L effective. Okay, scroll back to the past. L effective force BI L effective sine theta. Force BI L effective sine theta. The distance between the two edges, the direct distance, the shortest distance is only the new length of an curved magnet. Right? So, this is 30 degree, this is 30 degree, this is R. So, this is R sine of 30 degree, this is R sine of 30 degree. The total length is 2R sine of 30 degree. So, M dash is equal to M into L dash. So, that is small m into 2R sine of 30 degree. So, that is M into 2R. Sine of 30 is half, right? So, the new magnetic moment is going to be MR. But in option, we are not having MR. Suppose this is the length. In the formula L dash we have to take it. Right? In the formula, right, L dash we have to take. In the formula, guys, we have to take the L dash. So, MR. For this arc that extends the subtend, very simple thing. For whole arc, length is the circumference 2 pi r. 2 pi is an angle for whole arc. But when angle subtended by 60 degree, L is theta into R. 60 degree, it means pi by 3 into R. Can I replace it here? R is equal to 3L by pi. Can I replace it here? So M dash, it is going to be M into 3L by pi. Okay, so it is going to be 3 capital M by pi. That is the difference between the small m, capital M. This is the perfect answer for this specific question. Okay, this is the perfect answer for this specific question. Yes or no, guys? Sir, approximately 50 minutes of the lectures are going on. We have only moved on to the 3 to 4 sums. Okay, I told you all the quality of the sums are important. Okay, the students, those who are watching this lecture from the beginning, might have understood the actual difference. Okay, those who are watching this lecture from the beginning might have understood the actual difference into the beginning and into the last, right? They might have gone into the stream. They are like, oh sir, 40-50 minutes went on like that way. This happens since 9 years with me. It is not the first time, guys, right? All of the students used to say since 9 years, sir, this is only the class in which time went on, okay, and we are not aware of. Because things moves like this way, okay. I'm not showing off myself, okay, but this is the psychological reason, okay. Whenever you feel things quite interactive, time moves on. Similarly, when you are into the cinema hall, 3 hours move on. When you are watching the Netflix Game of Thrones, episodes moves on. Because you are feeling an interactive session with them. You are having a keen interest within it. So the physics teacher is having only responsibility to add a keen interest. Things moves on like that way. Yesterday one student comment, that was a very awesome thing for me. Okay, sir, I am able to solve these sums, but I am having very less speed and I am not able to cover up all of those sums into an examination for those number of the students. More you practice, more you gain the speed, more you practice, more you gain, right? Just hold on. Hello, sorry. The more you practice, the more you will gain, the more you will face the number of the varieties of question. The more you will face the number of the varieties of the question, the more you will have the confidence. The more you will have the confidence, the more you speed you will be having, right? So focus on more practice, guys. Okay, and for all of those number of the students, please don't mind. And see, if I'm discussing the comments right beneath the video, it doesn't means that, right, you should write the wrong comment, and it doesn't even means that I'm pointing out someone. Please don't sorry for that. Nah, this is a general and very healthy and a very productive discussion is going on between you and me. I'm trying to solve your problems. If it would be the live, then I could do like another way, right? If it would be live, I would do like another way. If it is not, the virtual session is going on, okay, so I am reaching I am having the comment one day after, and so I'm discussing the, right, this stuff. So please don't mind, yeah, you can, you're Indrajit sir, you and me, okay. See now again, a bar magnet having magnetic moment this, magnetic field this. The work done in, see, this was asked in 2009. Work done in taking the magnet slowly from 60 degree. Okay. WMB cos of theta 1 minus cos of theta 2. Immediately. Till now nothing has came from ferro, para and dia. Very simple questions are coming. Dia feebly attracted, ferro hardly attracted towards the magnetic like this. Question from hysteresis are coming. Okay, so this question is homework from my side. Now one question come up from JEE Main 2010. Magnetic moment for the diamagnetic atom. 0. I am giving you the answer. Diamagnetism is the universal property. This question is asked in mains. Now this shows the actual difference between the mains and the NEET. If I am going to tell you all the difference, you might forget someday. But I am requesting, I am giving you the answer. I am going to give you the explanation that diamagnetism is the universal property of the material that exists in all. In ferro, dia, para, everywhere diamagnetism is there. But you have to search it by yourself. So this is the previous one, and this question is homework from my side. Okay, you have to search it by yourself. Yes or no, guys? You have to search it by yourself a bit. Okay, because that will show you the difference now what we are moving on. Okay, now this here comes this another question. A current loop and external magnetic field. The question that was asked in NEET 2013. Here we are going to discuss, see, equilibrium conditions you all are aware of because you have seen into the 11th standard. In Newton's law of motion, you have seen the equilibrium conditions. Into work, energy and power, you have seen the equilibrium conditions. Into the rotational motion, you have seen the equilibrium conditions. Into the gravitation, you have seen the equilibrium conditions. Right? Everywhere you have seen the equilibrium conditions. This is kept in parallel to an external magnetic field. We all are aware of, right? Right now the angle is theta is equal to 0. Okay, the system is in equilibrium. Okay, only two types of equilibrium occurs. First, at theta is equal to 0. Second equilibrium occurs at theta is equal to pi. Here theta is 0. Okay, suppose it rotates, position is going to be same only, right? Position is going to be same only, but at theta is equal to 0, like this way, we are having the stable. Now it rotates by 180 degree. Okay, here previously it was like this, now it is getting rotated by 180 degree. Previously it was like this, kept in an external magnetic field, now it rotates by 180 degree. Okay, these are only the two positions where equilibriums are obtained. Okay, at theta is equal to 0, we are having the stable equilibrium, right? At theta is equal to pi, we are having unstable equilibrium. At theta is equal to 0, we are having the stable equilibrium. At theta is equal to pi, we are having the unstable equilibrium. So here also the position is different. Okay, external field is like this way only. Okay, but here the position is, suppose here I want to say this is A. Okay, then here we are having this is A. Like that. So sometimes instead of angles in question they are using, I want to rotate from stable to unstable. It means they are rotating from 0 to pi. In some, suppose they are saying, what is work done in rotating from stable to unstable? W is equal to mb cos of 0 minus cos of 180. This is a work done from rotating from stable to unstable. So that is equal to 2 mb. This much amount of the work is done. Stable to unstable. This is important. Okay. And in this, the question basis on time period of the oscillations are also asked. But that is moving on to the JE level. Okay. But I am giving you the reminder if it's okay. There is direct formula. Let me not move on to that. Okay. There is a direct formula. But for NEET purpose, this is only the important. A compass needle is kept which is allowed to move into the horizontal plane is taken to geomagnetic pole. This is earth, right? This is magnetic north. Sorry. That is magnetic. Rather than to write it down here, it is north and this is south. And these are the magnetic poles. Suppose here, if the needle is kept, here the horizontal component of the earth magnetic field is 0. We are having only vertical component. Okay. At magnetic poles, the horizontal component is going to be 0, vertical component is going to be non-zero. Vertical component will not have any torque on needle. So it is free to move. In any direction it can move. Wherever you will apply the force, it will move. Because here no torque is there, na? Vertical component is there. Horizontal component is 0. Okay. So here no one is going to create a torque. Okay. So here the answer is going to be, it will stay in any position. It will stay in any position. Yes or no, guys? Okay. Again, magnetic field is this. How much work is done? So I am going to give you all of this in homework. This is very simple. To protect a sensitive equipment, right? You have to keep inside the iron. Because inside the iron can, there is a vacant space. In vacant space, we are having no magnetic field. Okay, like electrostatic shielding we have seen into the electrostatics. If you are keeping the charge into the free space, okay, shield will occur. Similarly happens in this. If you want to protect the sensitive equipment, just have the area of iron in between, have the free space and keep the sensitive equipment within it. That's why they have named as iron can. Inside the can there is a space where we can keep the sensitive equipment. Okay. So students, thanks a lot for it, right? So this was all about the magnetism and matter, and I think it's time to go, right? Again, we're going to come back into the next lecture. So this is your own educator Indrajit Singh signing off from the desk. Bye bye, Sat Sri Akal and Namaste from my side. Bye everyone, stay at home, stay safe, stay healthy amidst this pandemic, and take care. Bye.